Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies following ancient light on its unhurried path through time. Tonight, our journey is called Quantum Physics, Explained Slowly. We're going to move gently, step by step, through the smallest mysteries of reality, as if listening to whispers beneath the stars. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe, no pressure at all. Before we drift further, you might take a slow breath and notice where you are. Perhaps you're lying in bed or resting on a couch. Maybe it is night where you are, or maybe daylight filters through curtains. Wherever and whenever you are, you're welcome here. Now dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. We begin under the velvet skies where the visible stars seem fixed, yet beneath them hides a story of the smallest possible scales. We tend to imagine the cosmos as vast beyond comprehension, stretching outward across deep time. But if we lean closer, if we look into the tiniest folds of matter and energy, we find another universe hidden within. That universe is quantum physics, a world not far away but here, woven into every breath, every photon of starlight, every grain of dust drifting across the Milky Way. Quantum physics does not announce itself loudly. It works in whispers, in faint fluctuations and probabilities. Beneath the quiet shine of stars, quantum laws quietly shape everything. The way atoms bind into molecules, the way light crosses the vacuum of space, the way stars fuse hydrogen into heavier elements. All of it rests on rules that are invisible to the naked eye. The most well-known mystery of this realm is uncertainty. But uncertainty here does not mean confusion or disorder. It means natural limit. A quiet boundary to what we can know. The very act of looking at a particle, the act of measuring, changes what can be said about it. This subtle rule, known as Heisenberg's uncertainty principle, hums beneath the fabric of all things. Imagine gazing at a star through a telescope. You think you see its position clearly. Yet if you were to focus on the tiniest particle of light from that star, you could know where it is, or how fast it moves, but never both with perfect clarity. The universe keeps a kind of secret, as though preserving its quiet. This idea might sound strange, but it is not chaos. It is the rule book. The universe allows patterns to emerge from uncertainty, like waves forming on a still pond. Out of these uncertain beginnings, galaxies, stars, and life itself rise. There are facts we know quite well. For example, hydrogen atoms make up nearly 3/4 of ordinary matter in the cosmos. Each hydrogen atom is governed by quantum rules, with its electron quietly orbiting the nucleus, not as a tiny planet, but as a shimmering probability cloud. This is mainstream knowledge, taught in every classroom, and yet hidden within that same hydrogen, astrophysicists still debate what happens when countless atoms interact at once, under immense pressure, deep in a star's core. Another detail, less known, is that the instruments we build to observe the sky often work at the edge of quantum noise. Radio telescopes listening for faint signals from deep space must cool their detectors almost to absolute zero. At such temperatures, the detectors are so sensitive they can pick up the gentle buzz of quantum fluctuations themselves. This is not poetic exaggeration. The instruments truly hear the faint hum of the universe's quantum breath. So when we talk about velvet skies and cosmic whispers, we are not speaking only in metaphor. There is an actual background murmur, a physical vibration of reality that every sensitive ear can detect if tuned well enough. This may leave you with a soft question. If the smallest scales of the universe are uncertain, how can the larger scales feel so solid? How can you rest your head on a pillow, feel the weight of gravity, and trust that the chair beside you will not dissolve into probability clouds? Physicists still debate the bridge between the quantum world and the everyday world, They call it decoherence, the process by which fragile quantum states fade into the stable patterns we know as reality. And so, as we lie beneath the velvet sky, we find that the stars above us, steady and serene, are built from laws that, at their root, are unsteady, uncertain, and whispered. To explain quantum physics slowly is to drift into this paradox without rushing, to let the tension between certainty and uncertainty become a kind of lullaby. As we move further tonight, we will keep circling these themes: tiny beginnings, vast consequences, whispered probabilities, cosmic certainties. For now, it is enough to notice that under the vast starlight the smallest rules are always present. They shape the glow of nebulae, the flicker of pulsars, the quiet orbit of planets. They shape your heartbeat too, the spark in your neurons, the patterns of warmth that let you rest. When we breathe with this awareness, the night feels even deeper. The velvet sky above is grand, but it is also within us, written in the hidden language of quantum physics. The vast sweep of the universe is usually imagined as an endless expanse of stars and galaxies, but if we drift back to the earliest moments, we find that what became galaxies and clusters began as something almost unimaginably small. The seeds of all cosmic structure were planted in the first instance after the birth of the universe, and strangely enough, those seeds may have been quantum in nature. Cosmologists speak of quantum fluctuations, tiny variations in energy and density that ripple across the very fabric of space. These were not grand, bright events, but faint tremors, softer than whispers, unfolding in the first trillionths of a second. Yet from those slight differences, the architecture of everything we now see was set in motion. It helps to picture a calm surface of water, disturbed only by the gentlest ripples. At first, nothing dramatic is visible, but if the water expands, those ripples stretch and grow, becoming larger patterns. In much the same way, the early universe swelled rapidly in what we call inflation, carrying tiny quantum ripples to cosmic scales. Those ripples later guided matter into filaments, clusters, and galaxies. We know, from precise observations of the cosmic microwave background, that these patterns exist. The faint variations in temperature across that ancient light are traces of quantum fluctuations stretched across space and time. That is a mainstream fact, something tested and measured. A lesser-known detail is how carefully we measure those ripples today. Satellites like Planck and WMAP mapped the sky with astonishing sensitivity, detecting changes in temperature as small as a few millionths of a degree. In that subtle pattern of warmer and cooler patches lies a record of the universe's earliest quantum breath. When you look at those maps, you're seeing the fingerprint of probability itself, frozen into the glow of ancient light. And yet, even with such clarity, questions remain. Astrophysicists still debate the details of inflation. Was it a single event, a sudden swelling that smoothed everything out? Or could it have been more complicated, perhaps even eternal, with new universes budding off from a quantum field that never truly settles? No consensus has been reached. The story of cosmic origins remains wrapped in mystery, and perhaps always will. But there is a quiet beauty in that uncertainty. We know enough to trace how faint fluctuations became galaxies, yet not so much that the wonder has faded. It leaves us suspended between knowledge and mystery, a place where the mind can rest as easily as it can question. Think for a moment of the Milky Way arching overhead. Its billions of stars are not scattered randomly. They are woven into a disk drawn together by gravity, flowing along filaments of dark matter. All of that complexity emerged from small beginnings. The bright clusters, the faint globulars, the spiral arms, they can all be traced back to quantum ripples that shaped the distribution of matter long before stars were born. Even closer to home, the Earth beneath you owes its existence to this story. Planets form in disks around stars, but the stars themselves and the clouds of gas that gave them birth followed paths laid out by quantum seeds. When you think of the chair beneath you, the air around you, the family of planets we orbit with, all of it is part of this quiet legacy. There is another soft detail worth noting. When astronomers study large-scale structure, the cosmic web of galaxies connected by filaments, they find a remarkable match between the observed distribution and the predictions made from quantum fluctuations. It is as though the universe kept a memory of its earliest whispers, and we are still living inside the shape they created. And yet, the connection is fragile. If inflation had lasted a little longer, or ended a little sooner, the distribution of galaxies might have been very different. If the initial quantum fluctuations had been larger, the universe might have collapsed into black holes before stars could form. If they had been smaller, matter might never have gathered into galaxies at all. Our existence balances on a knife edge of probability, written into the fabric of the earliest moments. To sit with this thought is not to feel anxiety, but to feel awe. The velvet sky above is not random. It is not inevitable either. It is the outcome of subtle whispers, amplified by expansion, guided by gravity, and spread across billions of years. So as we rest tonight, we hold in mind this gentle image. The entire cosmic web, every galaxy, every star, every world, grew from a quantum seed smaller than imagination, carried forward by the silent breath of inflation. The vastness above us began with uncertainty, yet unfolded into a universe that feels stable enough to hold us. We're left, again, in that space between knowing and wondering. We know the ripples are real, we see their traces in the ancient light. But what gave birth to them, what shaped the field that carried them, remains uncertain. Perhaps the answer lies beyond our horizon, or perhaps the universe, in its own way, is content to leave some questions open, like stars that shine just faintly enough to invite our curiosity without ever blinding us. When we turn our attention from the universe at large to the very heart of matter, we enter a landscape even stranger. Here, certainty begins to dissolve. Quantum physics reminds us that the smaller scales are never still, never entirely predictable. At their centre lies what is called the uncertainty principle, a quiet law that shapes every atom, every star, and every breath we take. Werner Heisenberg first described this principle in the 1920s. It tells us that there are pairs of properties, like position and momentum, that cannot be known with perfect precision at the same time. The more clearly you fix one, the more softly the other fades away. If you know exactly where a particle is, its momentum becomes a blur. If you pin down its momentum, its position smears out into probability. This is not about faulty instruments. It is about the nature of reality itself. Think of watching a firefly on a summer night. When it hovers in one place, you cannot see how fast it moves. When it darts quickly, you can no longer fix exactly where it is. The firefly is not the particle, but the image can help us drift into the feeling of uncertainty. At the quantum level, this is not just a limitation of vision, but a rule of the universe. This principle is not merely an abstract curiosity. It explains why atoms do not collapse, why matter is stable. Electrons cannot sit perfectly still at the nucleus. Uncertainty keeps them in motion, spread out in shimmering clouds. Because of this, atoms occupy space. Because of this, your hands cannot pass through the chair beside you. The solidity of the world emerges from uncertainty. A mainstream fact is that the uncertainty principle sets a minimum scale for what we can measure. Even the best instruments on Earth, like the detectors used in the LIGO Observatory to sense gravitational waves, must contend with quantum uncertainty. The mirrors that reflect laser beams there move by distances smaller than a proton, and even those movements are shadowed by quantum noise. The most delicate measurements we make are forever shaped by the same rule that keeps atoms intact. A less widely known detail is that astrophysicists must also contend with this limit when studying the cosmos. For example, when detecting faint light from distant galaxies, quantum fluctuations in the detectors themselves set the ultimate boundary of precision. Even the most advanced telescopes orbiting far above Earth's atmosphere can only collect so much certainty before they are gently reminded of the rule: there is always a limit. And yet, what lies beyond the rule remains debated. Some physicists argue that uncertainty is woven into the deepest structure of space-time. Others suggest it might arise from hidden variables we cannot yet see. The mainstream view is that uncertainty is fundamental, but even here, humility remains. The debate continues quietly in laboratories and lecture halls, a reminder that our grasp of reality is never complete. What makes this law so calming, in its own way, is that it balances the universe. If there were no uncertainty, electrons might collapse inward, matter might fall apart, and the cosmos could not exist as it does. Instead, uncertainty provides breathing room. It creates stability out of motion, a paradox that becomes harmony. When you look at the night sky, every point of starlight is sustained by this principle. The fusion reactions inside stars depend on quantum tunneling, which in turn is guided by uncertainty. The fact that stars shine steadily for billions of years is not in spite of uncertainty, but because of it. Imagine for a moment that you could hold a grain of sand in your palm. Within that grain are countless atoms, each one governed by the uncertainty principle. Each electron is both particle and cloud, both somewhere and everywhere. The grain is ordinary, yet inside it lives the same quiet rule that shaped galaxies. And here we are, resting under velvet skies, reminded that solidity and stability are not the absence of uncertainty, but its gift. Without it, there would be no earth, no breath, no chance for you to hear these words. Astrophysicists may continue to debate whether uncertainty is the final word or just a doorway into deeper truths, but for us tonight, it is enough to drift with the knowledge that the unsteady heart of matter is also its strength. What looks like fragility becomes endurance. What seems like a limit becomes the reason we exist. If uncertainty is the heartbeat of quantum physics, then superposition is its quiet breath. This principle tells us that particles are not simply in one state or another, but can rest in a blend of possibilities until observed. To the everyday mind, it may sound impossible, yet the universe whispers it constantly. Think of the night sky, where faint beams of starlight drift toward us across millions of years. Each photon can be described not as following a single path, but as existing in a haze of paths at once, like overlapping trails of mist. Only when the photon is measured, when it strikes a detector or the back of your eye, does one path emerge as real. Until then, it is a quiet superposition of all possibilities. The most famous illustration of this principle comes from the double-slit experiment. When particles such as electrons or photons are sent through two narrow openings, they do not behave as tiny marbles choosing one slit or the other. Instead, they spread like waves, interfering with themselves, creating a pattern of bright and dark fringes on a screen. The strange part is this: even when particles are sent one at a time, the interference pattern still emerges, as though each particle is travelling through both slits at once. This is a mainstream fact taught in physics classrooms and confirmed by countless experiments. It is not theory alone. It is a direct observation, repeated so many times that it has become one of the most reliable truths in science. And yet the interpretation remains uncertain. Does the wave of probability represent something real, or only our knowledge of the system? Does the act of measurement collapse the superposition, or is reality constantly branching into many possible worlds, all unfolding silently in parallel? Astrophysicists and philosophers alike still debate these questions. A quieter, less known detail is how superposition is tested at larger scales. In laboratories, researchers have coaxed not just photons or electrons, but entire molecules into superposition states. Some of these molecules are made of hundreds of atoms, complex enough to remind us of everyday matter. They drift in quantum haze, occupying overlapping paths before collapsing into a single outcome. This shows us that superposition is not confined to the smallest particles. It can reach into the realm of the ordinary, though it becomes fragile there, easily broken by interaction with the environment. The fragility of superposition is important. In the vastness of space, conditions sometimes preserve quantum states longer than they survive on Earth. In the cold vacuum between stars, isolated particles can remain in delicate superpositions for astonishing spans of time, untouched by the bustle of collisions that fill our planet's atmosphere. Out there, probability waves stretch and linger, unobserved, and so, as we gaze at the Milky Way's shimmer, we might imagine countless quantum states still suspended, awaiting collapse, like overlapping chords waiting to resolve into harmony. The stars themselves, though steady to our eyes, are born of processes rooted in this haze of possibilities. One way to rest with this thought is to picture two soft beams of moonlight crossing a window pane. You do not need to decide which beam you see, for both rest together in the quiet of the night. Superposition is like that, but deeper, particles overlapping with themselves, suspended in a state that is neither one thing nor the other, but both, until gently resolved. The debates about meaning continue. Some physicists argue that superposition is a sign of reality's inherent probability. Others suggest that multiple universes bloom with each outcome, splitting endlessly. Still others propose hidden mechanisms that we have not yet glimpsed. The discussions unfold with care, but no consensus has been reached. What is clear is that superposition shapes the world we know. Without it, electrons could not bind atoms into molecules. Without it, chemistry as we understand it would not exist. The very fact that your body is held together by molecules depends on the same quiet principle that makes photons draw interference fringes across a screen. So tonight, as we breathe beneath velvet skies, we can let superposition be less a riddle and more a comfort. It reminds us that reality is not rigid but soft, not locked but open. Possibility rests at the heart of everything. What looks to us like stability is the resolution of many overlapping options, harmonized into one quiet outcome. The stars above you, the warmth of your room, the pulse of your heart, all of it carries this legacy. We are not strangers to superposition. We are born from it, sustained by it, and perhaps always surrounded by its unseen haze. Entanglement is perhaps the most dreamlike of all quantum ideas. It tells us that two particles can become linked in such a way that their states are no longer separate. Even if the particles drift light years apart, their properties remain connected, as though joined by an invisible thread across quiet horizons. When we speak of entanglement, we do not mean a metaphor. Experiments confirm that when two entangled particles are measured, the outcome of one is tied instantly to the other, no matter the distance. This is a mainstream fact, tested again and again. What startled Einstein, Podolsky and Rosen in the 1930s remains true today. It led Einstein to call the phenomenon spooky action at a distance, a phrase that still lingers in our imagination. To picture it gently, imagine two fireflies drifting apart into the night. You might expect them to blink in their own rhythms, but if they are entangled, their lights are linked. When one shines bright, the other dims, even if they're separated by forests or oceans. The link is not carried by a signal we can see. It is simply there, written into the shared state of both. Less known outside physics circles is the way entanglement is used to test the very foundations of reality. In laboratories, scientists measure correlations between entangled particles and compare them against what would be possible under classical rules. The results consistently violate those classical limits, showing that no local, hidden variable explanation can account for what we see. The experiments are delicate, often using polarized photons or spins of atoms, and they reveal that the universe is not bound by the rules of separateness we take for granted. Astrophysicists are even exploring whether entanglement could be tested on cosmic scales. Some proposals suggest using photons from distant quasars as random triggers in entanglement experiments, ensuring that any hidden influence would have to stretch back billions of years. In this way, the universe itself becomes part of the test, its ancient light serving as a witness to quantum strangeness. And yet, even as the facts accumulate, the meaning remains uncertain. Physicists still debate what entanglement truly implies. Does it mean information travels faster than light? Or does it mean that distance itself is not what we think it is? Is reality fundamentally non-local, or are we glimpsing only part of a deeper structure we cannot yet name? The questions linger, unanswered. Entanglement is not just a curiosity, it is a resource. On Earth, researchers harness it for quantum communication, creating systems where information can be transmitted with security guaranteed by the laws of physics themselves. Entanglement also forms the backbone of quantum computing, where linked qubits can perform calculations far beyond the reach of classical machines. But tonight, resting under a velvet sky, we can let go of applications and let the wonder remain. If you think of the stars spread across the horizon, each one separated by light years, you can imagine threads of entanglement stretching between them, unseen, unbroken. Not because those specific stars are entangled, but because the universe itself may carry a hidden fabric where separateness is never absolute. To breathe with this thought is to soften into connection. Perhaps the molecules in your body once forged in a distant star carry a kind of memory of entanglement. Perhaps the quiet harmony between particles is not a trick, but the foundation of belonging. And so, we drift with the idea that across quiet horizons, there are links we cannot see but that may always remain. Entanglement reminds us that distance is not the final word, that separateness is not complete. In the quantum hush, all things may be more connected than they appear. The night sky teaches us to see light as both wave and point. Stars glitter like sharp particles, yet their glow spreads in ripples across the heavens. This quiet duality lies at the heart of quantum physics, where light and matter reveal themselves as both wave and particle, depending on how we look. This is called wave-particle duality, and it has been confirmed in countless experiments. Photons behave like discrete packets of energy when they strike a detector, but they also spread out like waves when passing through narrow slits. Electrons, too, show the same double nature. They are particles with measurable mass, yet they diffract and interfere like water waves. To picture this, imagine moonlight reflecting on a still lake. The silver path shimmers with countless points of brightness, yet the whole reflection drifts as a single wave. At the quantum level, every particle carries this dual aspect, flickering between the sharp and the diffuse. A mainstream fact is that this duality is not just a quirk of light, but of all matter. Even large molecules, when cooled and isolated, have been observed to create interference patterns as if they were waves. The rule holds across scales, though the effect grows harder to preserve as size increases. A lesser-known detail comes from astronomy itself. Telescopes that detect faint starlight must account for the dual nature of photons. Instruments like the James Webb Space Telescope gather light that has travelled for billions of years. Each photon arrives as a particle, delivering a tiny click of energy. But the image that builds with its fine interference and diffraction patterns is evidence of the wave nature. In this way, wave-particle duality is woven into every astronomical observation we make. And still, the debate remains open. Physicists continue to ask whether light is truly both things at once, or whether the distinction arises only from how we measure. Some interpretations suggest that the particle and wave are two sides of one underlying reality, glimpsed differently depending on our perspective. Others hold that the universe itself does not commit to one description until interaction forces its hand. This quiet ambiguity, rather than confusion, can feel like a gift. The universe offers us more than one way to see it, and both are valid. Sometimes light is a sharp particle, tracing a line through space. Sometimes it is a soft wave, spreading wide, overlapping with others. Reality can hold both without contradiction. When you gaze at the Milky Way arching overhead, you are seeing the harmony of this dual nature. The stars twinkle because photons arrive in discrete bursts, while the faint glow of nebulae spreads like mist, carried by waves. Both experiences rest on the same principle. Both are true at once. Even here, on Earth, this duality shapes our lives. The electronics that power your phone, your computer, even the device through which you hear these words rely on quantum behavior born from wave-particle duality. Semiconductors work only because electrons can act as waves, tunneling and overlapping, guiding current through materials. To rest with this thought is to soften into paradox. The universe does not demand a single answer. It offers both. A photon can be a particle, a wave, or something deeper we cannot yet describe. Our understanding drifts between images, and reality holds them both. As you breathe tonight, you might imagine light as ripples across a velvet pond, and also as single sparks that leap across the dark. Both belong. Both are part of the same quiet truth. The cosmos, like the mind, allows more than one story at once. If we drift deeper into the fabric of reality, we encounter the idea of fields, gentle, invisible structures that extend everywhere, carrying energy and guiding particles. In quantum physics, particles are not separate, isolated objects. They are excitations, tiny ripples, in fields that span the cosmos. The photon is a ripple in the electromagnetic field. The electron is a ripple in the electron field. Every particle has its corresponding field, and those fields weave together to form the quiet stage of the universe. What we call matter and energy are patterns of vibration within this unseen fabric. A mainstream fact is that the most successful model of particle physics, known as the Standard Model, describes these fields with exquisite precision. It predicts how particles interact, how forces are carried, and even accounts for subtle effects that have been measured to incredible accuracy. The discovery of the Higgs boson in 2012 confirmed that the Higgs field exists, a field that grants mass to fundamental particles. Without it, matter could not take shape, and stars and planets would never have formed. But beyond these well-tested ideas lies mystery. A lesser-known detail is that the Higgs field is thought to have a non-zero value even in empty space. That means that even when you imagine a perfect vacuum, the Higgs field is there, humming softly, giving particles their mass. The universe, even at its quietest, is not truly empty. And yet, astrophysicists and cosmologists still debate how these quantum fields connect with the large-scale structure of space-time. Do they exist independently, floating on the canvas of the cosmos? Or are they inseparable from the geometry of space itself, woven into the same fabric that curves around stars and galaxies? We do not yet know. When you look up at the velvet sky, you're not only seeing stars, but also sensing the presence of fields that hold everything together. The glow of a nebula is light rippling through the electromagnetic field. The structure of atoms is bound by fields of force that never turn off. Even the warmth you feel in your skin comes from interactions between fields, steady and constant. Imagine the fields as an invisible ocean, stretching without shore. Particles are like ripples on its surface. They rise and fall, they interact, they fade, but the ocean itself remains. It is everywhere, carrying the quiet murmur of quantum reality. Here on Earth, we have learned to tap into these fields in subtle ways. Radio waves are gentle ripples in the electromagnetic field, carrying voices and music across the air. MRI machines in hospitals use magnetic fields to pierce softly into the body. Lasers, solar panels, fiber optics, all rest on our understanding of quantum fields. Yet no matter how familiar their effects, the essence of fields remains abstract, intangible. We cannot see them directly, only their influence. They are like the hush of the night, present everywhere, even if unnoticed. Astrophysicists wonder if other unknown fields may still exist. Could dark matter be the ripple of a field we have not yet discovered? Could dark energy, the force pushing the universe to expand ever faster, arise from the quiet background of a hidden field? These questions remain open, as vast as the sky itself. For now, we can rest with the thought that the universe is not a void scattered with isolated dots. It is a sea of fields, softly vibrating, carrying every particle, every breath, every star. Beneath the quiet shimmer of starlight lies a deeper hush, the hum of invisible oceans we're only beginning to understand. When we imagine a vacuum, we might picture absolute emptiness, a space stripped of air, light and matter. But in quantum physics, the vacuum is never truly empty. Even in the deepest void between galaxies, space is alive with faint fluctuations, a background hum of activity that never fully fades. This is because of what is called zero-point energy. According to quantum theory, every field in the universe must always carry some minimum energy, even when no particles are present. The vacuum is a restless sea, where particles and antiparticles flicker in and out of existence, borrowing energy for brief moments before dissolving back into silence. This is not just speculation. A mainstream fact is that the Casimir effect provides direct evidence of these fluctuations. When two metal plates are placed very close together in a vacuum, they experience a gentle force pulling them together. This arises because the quantum vacuum between the plates holds fewer possible fluctuations than the space outside, creating an imbalance. The plates are nudged, not by ordinary matter, but by the quiet breath of empty space itself. A lesser-known detail is that astrophysicists must consider vacuum energy when thinking about the universe's expansion. Some suggest that the mysterious dark energy driving cosmic acceleration might be linked to the energy of the vacuum. Yet when physicists calculate the expected vacuum energy from quantum fields, the numbers come out vastly larger than what we observe, by factors of trillions upon trillions. This mismatch, called the cosmological constant problem, is one of the deepest puzzles in modern science. Here is where the debate continues. Some argue that we are missing a piece of physics, something that cancels or balances the vacuum energy in ways we do not yet understand. Others wonder if the very concept of space-time needs to be rethought, that perhaps what we call empty space is woven from a deeper hidden order. The truth remains uncertain, a reminder that even the most silent parts of the cosmos are filled with mystery. When you gaze into the velvet sky, know that the darkness between stars is not a void. It is a living fabric, humming with unseen fluctuations. The photons that reach us must cross this restless sea, nudged ever so slightly by the vacuum-shifting energy. Even here on Earth, we live within this invisible presence. Every atom, every interaction, is influenced by the vacuum. Without it, the laws of physics as we know them would unravel. The very structure of the universe depends on the quiet murmur of something we cannot see. To imagine it gently, think of a darkened room. At first it seems still, but if you wait, you hear faint sounds. A fan humming, a floorboard settling, the distant whisper of the wind. The vacuum is like that. It is never silent, never completely still. Beneath the calm there is always a hidden vibration, a song of probability that never stops. And so, as we drift beneath starlight, we may find comfort in this idea. The cosmos, even in its darkest corners, is never barren. It is alive with the breath of quantum fields, a subtle reminder that stillness is not emptiness. The velvet black between stars is full of motion, too soft for our eyes but always there. When we drift back to the very beginning of time, to the first flicker after the Big Bang, we find that quantum physics may have guided the universe's earliest dawn. The expansion known as inflation swelled space faster than light could cross it, smoothing the cosmos and stretching quantum fluctuations to cosmic scales. From these faint seeds, the first structures of the universe began to form. This is why cosmologists sometimes say the universe has quantum origins. Without those tiny fluctuations magnified by inflation, matter might never have gathered. Stars might never have formed. The galaxies we see scattered across the night sky would not exist. The quiet patterns we live within began in a haze of uncertainty. A mainstream fact is that evidence for this lies in the cosmic microwave background, the faint afterglow of the Big Bang. Satellites such as COBE, WMAP and Planck have mapped this background in exquisite detail, showing tiny variations in temperature. Those patterns are the stretched fingerprints of quantum ripples from the universe's earliest moments. A lesser-known detail is that scientists also search for even subtler traces, patterns of polarization in the microwave background. If found, they could reveal gravitational waves created during inflation, carrying direct proof of quantum fluctuations imprinted on the fabric of space-time itself. These patterns, called B-modes, are faint and difficult to detect, but they remain one of the most sought-after signals in cosmology, and yet much remains uncertain. Astrophysicists debate whether inflation truly occurred, or whether other processes might explain the smoothness of the universe. Some theories propose a bouncing cosmos, where contraction preceded expansion. Others suggest that inflation could be eternal, spawning countless bubble universes in a vast multiverse. No final answer has been reached. Still, the idea that our universe emerged from quantum whispers is humbling. Imagine space less than a fraction of a second old, already carrying the patterns that would one day become clusters, stars, and even us. Out of silence, out of fluctuation, came everything. When you look at the velvet sky, you are seeing the long aftermath of that dawn. The galaxies shining back at us are the matured forms of those first ripples. Even the atoms in your body are part of this unfolding. The carbon in your cells, the oxygen you breathe, all trace back to stars that would not exist without those initial quantum seeds. To hold this thought is to rest in connection. The small and the vast, the uncertain and the solid are bound together. The dawn of time and this quiet moment now are linked by a thread that has never broken. And so, as we breathe beneath starlight, we can imagine the universe as a child of quantum possibility. Its earliest moments were fragile, uncertain, yet those very qualities gave rise to the cosmic order we now see. What seems improbable, almost impossible, is the reason we exist. The quantum dawn is not only behind us, its echoes remain in every star, every world, every heartbeat. The beginning still whispers through the present, as softly as starlight crossing a window pane at night. If we listen carefully to the silence of the night sky, we find that it is not truly silent. The universe still carries a faint glow from its earliest days, a soft radiation known as the cosmic microwave background. This afterglow is the oldest light we can see, stretched thin across the heavens, a record of when the universe was only 380,000 years old. At that time, the cosmos had cooled enough for protons and electrons to join and form neutral hydrogen. Before then, light could not travel freely, as it was constantly scattered by charged particles, but with atoms formed, the fog lifted, and photons began their long journey. Those ancient photons are still arriving now, bathing the universe in a whispering background glow. A mainstream fact is that this radiation is measured with remarkable precision. It has a temperature of about 2.7 degrees above absolute zero, nearly uniform across the sky, but not perfectly uniform. Tiny fluctuations in the background, differences as small as 1 part in 100,000, hold the imprints of early quantum ripples stretched across space during inflation. A lesser-known detail is how scientists capture this ancient light. The detectors aboard satellites like COBE, WMAP and Planck must be cooled to near absolute zero to avoid adding their own heat to the signal. They are so sensitive that they can measure temperature variations smaller than a millionth of a degree. In these faint patterns lies a cosmic map, showing where matter would later gather into galaxies and clusters. And yet, even with all this clarity, questions remain. Astrophysicists still debate whether the patterns we see contain signs of primordial gravitational waves, ripples in space-time from the earliest moments. If detected, such waves would confirm that quantum fluctuations not only shaped matter, but also stirred the fabric of space itself. So far, hints have appeared, but no final proof. The search continues. To imagine this glow, picture a night where the stars are hidden by clouds. The darkness seems complete, but behind it, a soft light still lingers, too diffuse to see directly. The cosmic microwave background is like that. It surrounds us everywhere. A hidden sky beneath the visible one. Every time you look up at the Milky Way, you are seeing light layered upon older light. The twinkle of stars rests upon the quiet glow of galaxies, and beyond them, the invisible background hum of the universe's first light. The velvet sky holds all these layers at once, overlapping like a faint harmony. Here on Earth, the same radiation passes gently through us. Radio telescopes that map the background are not catching exotic signals from elsewhere. They are catching the constant rain of ancient photons that bathe every atom, every moment. You are right now immersed in this quiet glow, even if you do not feel it. And so, the cosmic microwave background becomes a reminder of connection. It is the oldest message we can hear, not written in words, but in temperature and pattern. It is the universe itself telling its story softly across 13 billion years. The next time you stand beneath the night sky, you might imagine that faint afterglow, invisible to your eyes but always there. You're not only looking into the present stars, but resting within the memory of the universe's earliest light. Among the most mysterious places in the universe are black holes, regions where gravity is so strong that nothing, not even light, can escape. To the eye, they appear as silent voids, yet quantum physics suggests they are not entirely black. Even here, at the edge of nothingness, quantum whispers may be heard. Stephen Hawking showed that black holes can emit a faint glow, now known as Hawking radiation. It arises from quantum fluctuations at the event horizon, the boundary that marks the point of no return. In the quantum view, pairs of particles are constantly flickering into existence, borrowing energy from the vacuum before annihilating one another. Near the horizon of a black hole, one particle can fall inward while the other escapes. To an outside observer, it appears as though the black hole is emitting radiation. This is a mainstream fact in theoretical physics, though it has not yet been directly observed. If true, it means that black holes are not eternal. Over vast timescales, they slowly lose mass and eventually evaporate into nothing but radiation. A lesser-known detail is how incredibly faint this radiation would be for large black holes. For a black hole with the mass of the Sun, the temperature of Hawking radiation would be less than a millionth of a degree above absolute zero, far colder than the cosmic microwave background that surrounds it. This makes detection nearly impossible with current instruments. Only tiny black holes, far smaller than stars, would radiate strongly enough to be seen. None have yet been found. And yet, the debates are far from settled. Physicists still argue over what happens to information that falls into a black hole. Does it vanish forever, violating the rules of quantum mechanics? Or is it somehow preserved, encoded in subtle patterns of radiation, or perhaps stored on the horizon itself like a cosmic hologram? This puzzle, called the information paradox, remains one of the most pressing mysteries at the intersection of gravity and quantum theory. To rest with this thought is to realize that even the darkest places may not be silent. What appears to be emptiness may still carry a faint whisper of light. The The velvet horizon of a black hole may glow softly with radiation too faint for us to see, yet powerful enough to challenge our understanding of physics. Imagine lying beneath the stars, thinking of a black hole at the center of a galaxy. Around it, stars orbit in long, graceful arcs. Gas swirls and heats, shining brightly before crossing the horizon. Beyond that line, we see nothing. And yet, the quantum rules suggest that the horizon itself is alive with activity, with pairs of particles flickering in and out, some escaping, some consumed. Even there, uncertainty and fluctuation remain. We do not yet know the full truth. Astrophysicists debate whether space-time itself breaks down at the heart of a black hole, or whether some new physics emerges that we cannot yet name. But what we do know is enough to invite awe. The darkest regions of the cosmos are not silent voids, but stages where quantum whispers still play. So tonight, as we rest under starlight, we might imagine the universe as a balance between vast gravity and subtle quantum breath. Even in the places where light disappears, there is still a story, still a quiet glow, still a question waiting to be answered. The stars that shine so steadily above us are powered by a process that relies on one of quantum physics' most delicate tricks. Deep in their cores, hydrogen atoms fuse into helium, releasing light and heat that drift across the velvet sky. Yet at the temperatures inside a star like our Sun, the protons should not have enough energy to overcome their mutual repulsion. By classical rules, the fusion fires should not burn as brightly as they do. This is where quantum tunneling enters. It allows particles to slip through barriers they do not have the energy to climb over. Protons in a star's core, though too weak to overcome their electrical repulsion outright, sometimes tunnel through it, merging to begin the chain of fusion. Without this quiet bending of the rules, stars might never shine, and the cosmos would remain dark and cold. A mainstream fact is that tunneling is a direct consequence of quantum mechanics. It does not mean particles ignore barriers completely. Rather, it means there is always a small probability of them appearing on the other side, even when classical physics sees it as impossible. Over billions of protons, that small chance becomes a steady source of energy. A lesser-known detail is that tunneling shapes not only the hearts of stars but also technologies here on Earth. The scanning tunneling microscope, for example, uses electrons tunneling across a tiny gap to create images of surfaces at the scale of individual atoms. Devices like flash memory also rely on tunneling to trap and release charges in delicate layers of material. And yet, the meaning of tunneling remains open to interpretation. Physicists still debate whether it is best understood as a particle literally passing through a barrier or as a wave function extending into forbidden regions until it finds a way through. The mathematics is clear, but the story beneath the math remains uncertain. To imagine it gently, think of a stream running against a rock. Most of the water flows around, but sometimes droplets find tiny cracks and seep through, appearing on the other side. In quantum mechanics, even when the rock seems solid, there is always a chance of a droplet slipping through. The universe itself has built this possibility into its foundations. When we look up at the stars, we are looking at tunneling in action. Every photon of starlight that reaches your eye tonight is the child of a tunneling event in the heart of a star. Without that fragile probability, there would be no sunlight, no warmth, no life. Even in the quiet of your body, tunneling plays a role. Enzymes that guide chemical reactions sometimes rely on particles tunneling between atoms, allowing processes to happen far faster than they would otherwise. Life itself seems to borrow this trick, as if evolution learned to whisper in the language of quantum rules. And so, tunneling becomes a reminder of fragility and strength combined. The stars shine because of an improbable process, yet they burn steadily for billions of years. Life flourishes because of delicate pathways, yet it endures. The improbable becomes the foundation of the possible. Tonight, as we drift under velvet skies, we might feel comfort in this paradox. Barriers may seem insurmountable, yet the universe allows quiet passages through. What looks impossible can still occur, not by force, but by probability, by softness, by a hidden door that opens without sound. The atoms that build our world, the molecules that shape air, water and life itself, all rest on quantum rules. Chemistry is, at its heart, quantum physics beneath starlight. Without the strange behaviour of electrons, the periodic table would lose its structure, bonds would not form, and the cosmos would remain a scattering of lifeless gas. Electrons do not orbit nuclei like planets around a star. Instead, they form clouds of probability, patterns called orbitals. These shapes, spherical, dumbbell-like, or more intricate, determine how atoms connect. Quantum mechanics dictates that only certain energy levels are allowed, and that electrons must settle into these states like notes in a cosmic scale. A mainstream fact is that these rules explain the variety of elements. Hydrogen, with 1 electron, behaves differently from oxygen with 8. Carbon, with its 4 valence electrons, can form chains and rings, the backbone of complex molecules. Silicon, just below carbon in the periodic table, follows similar rules, allowing us to build computers from its quiet conductivity. A lesser-known detail is how quantum chemistry extends beyond Earth. In the cold clouds of interstellar space, molecules as complex as amino acids have been detected. Radio telescopes tuned to precise frequencies can pick out the spectral signatures of these molecules, showing that the chemistry of life has cosmic roots. The quantum bonds that hold proteins together on Earth are the same bonds forming quietly in nebulae light years away. And yet, debates remain. Astrophysicists and chemists still wonder how far quantum effects stretch into biology. Some propose that quantum tunneling or coherence plays a role in processes like photosynthesis, or even in the way birds navigate using Earth's magnetic field. These ideas remain open, uncertain, and softly compelling. To imagine quantum chemistry, think of a chord played on a piano. Not every note is possible, only those that fit within the instrument's keys. Electrons follow similar rules. They cannot rest anywhere, only in allowed states, and when they jump between them, they release or absorb light. Every photon from a star, every colour in a nebula, comes from such quiet transitions. The very breath you take reflects these laws. Oxygen binds with hemoglobin in your blood because of the way electrons arrange themselves. Water flows because hydrogen bonds, faint but steady, link molecules together. DNA, carrying the instructions of life, is held in its double helix by the stacking of quantum bonds, and in the wider cosmos the same chemistry unfolds. The Orion Nebula glows not only with light from young stars, but also with the spectral lines of molecules forming in the gas around them. The icy moons of Jupiter and Saturn may harbour oceans rich in chemistry, stirred by quantum rules no different from those here on Earth. As we rest under the velvet sky, it is humbling to remember that the laws shaping galaxies also shape the molecules within us. The periodic table with all its structure is a quiet expression of the quantum world. It shows us that order can emerge from uncertainty, complexity from simplicity, life from possibility. Perhaps the most comforting thought is that chemistry is not confined to one planet. It is a cosmic process, unfolding everywhere. The bonds in your body and the bonds in distant clouds of gas are kin, born of the same quantum dance. The universe writes its poetry in electrons, orbitals and bonds, and life is one of its verses. Life, as we know it, is built on chemistry. Yet there are hints that quantum physics may whisper within biology too, guiding processes in ways that seem improbable under classical rules. The boundary between physics and life is not sharp but softly blurred, as though nature carries the same language across scales. A mainstream fact is that photosynthesis, the process by which plants and some bacteria harvest light, shows signs of quantum coherence. When photons are absorbed, their energy must be carried through a maze of molecules to reach the reaction center where it is stored. Experiments suggest that the energy does not take a single path but moves as a wave, exploring many routes at once, like a quantum superposition. This allows the energy to find the most efficient pathway, a quiet echo of quantum rules helping leaves turn sunlight into food. A lesser-known detail is that migratory birds may also use quantum effects. Some species navigate by sensing Earth's magnetic field, and one hypothesis is that this sense depends on entangled electron pairs in molecules within their eyes. The magnetic field might influence the reactions, letting the birds perceive orientation in ways that classical physics struggles to explain. If true, their long migrations across velvet skies are guided by quantum threads we are only beginning to glimpse, and yet the extent of quantum biology remains uncertain. Researchers debate how long delicate quantum states can survive in the warm, noisy environment of living cells. Some argue that coherence quickly fades, too fragile to play a significant role. Others believe life has evolved ways to preserve and even use this fragility, weaving quantum rules into the machinery of existence. The question remains open, waiting for clearer experiments and gentler understanding. To rest with this thought, imagine photosynthesis at dusk. A single photon, having travelled from the sun, strikes a leaf. Its energy slips into a network of molecules, spreading like ripples in water, probing many paths at once before settling into the most efficient route. In that moment, quantum probability feeds the quiet growth of life. The same might be happening inside your body. Enzymes sometimes rely on tunneling, allowing protons or electrons to pass through energy barriers that classical rules would forbid. These tiny shortcuts make reactions faster, efficient enough to sustain the constant processes of living cells. Without them, metabolism would slow to a crawl, and life might not thrive at all. Even in the molecules that carry your thoughts, quantum rules appear. The proteins that shape your brain's activity, the chemistry that underlies memory and awareness, are built from bonds that follow the same rules as distant starlight. Though we cannot yet say how far quantum effects reach into the mind, the possibility lingers, like a star just below the horizon. As we breathe beneath the velvet night, we may find comfort in this continuity. The laws that shape galaxies also whisper in leaves, wings, and cells. Life does not stand apart from the cosmos, but grows out of it, rooted in the same quantum soil. Perhaps this is why starlight feels familiar. The photons warming your skin once danced through the same rules that guide photosynthesis and vision. The quantum world does not stop at the edge of atoms. It extends into every breath, every heartbeat, every migration of birds across quiet skies. When we think of time, we usually imagine it flowing in a single direction, from past to future, carrying us forward like a river. Yet quantum physics offers a softer, stranger picture, where time's arrow is less certain, and where reversals are not impossible in theory. At the heart of quantum equations, time often appears symmetrical. The laws that describe particles and waves can be run forward or backward with equal validity. If you watch them like a film reel, you could reverse the reel, and the math would still work. This symmetry suggests that the universe itself may not prefer one direction of time over another. A mainstream fact is that the arrow of time we experience is tied to entropy, the tendency of systems to evolve from order to disorder. In the early universe, entropy was low. Over billions of years, stars burned, galaxies spread, and order gave way to more complexity and disorder. This increasing entropy gives time its apparent flow. A lesser-known detail is that in certain quantum processes, particles can appear to move backward in time. In Feynman diagrams, for example, an electron travelling backward in time can be described as its counterpart, the positron moving forward. While this is a mathematical tool, it raises deep questions about whether time's direction is as absolute as it feels, and yet the the debates remain. Physicists argue over why the universe began with such low entropy, and whether time's arrow is a fundamental feature of reality or only an emergent one. Some theories propose that on the larger scales, time may be cyclical, or even that different regions of the universe might experience different arrows. These ideas remain uncertain, and perhaps always will. To imagine this gently, think of ripples on a pond. Drop a pebble and the ripples spread outward. But in theory, if you could reverse every motion precisely, the ripples would converge back, the pebble would leap into your hand, and the pond would be still again. The laws allow it, though in practice the noise of the world ensures it never happens. Our experience of time is not only physical but deeply human. We measure it in heartbeats, in seasons, in the turning of Earth beneath the stars. But beneath that experience, quantum rules suggest a more flexible picture. Perhaps the arrow of time is not fixed but softly drawn, a tendency rather than a command. Even in the cosmos, this openness lingers. Black holes challenge our notions of time, slowing it near their horizons. Expanding space stretches time itself, so that distant galaxies drift into our future as much as our past. Gravitational waves ripple through time, bending its flow. And at the quantum level, time sometimes seems to hesitate, to shimmer, to allow possibilities where direction is unclear. As we rest beneath velvet skies, we might take comfort in this uncertainty. The arrow of time carries us forward, yes, but its foundation is softer than we once believed. The past and future may be less divided than they seem, connected through quantum rules that allow echoes to drift both ways. Perhaps this is why memory and anticipation feel so alike, one a quiet record, the other a quiet hope. The universe itself may weave them together, its quantum fabric holding time not as a line but as a haze. And so, as we breathe, we can let time's mystery be less a puzzle and more a lullaby. Its arrow may not be strict, but its flow carries us gently, like starlight drifting across horizons, unhurried, without end. If superposition shows us that particles can rest in many states at once, and uncertainty tells us there are limits to what we can know, then decoherence explains why the world feels stable in spite of these quantum rules. It is the quiet process by which fragile quantum states fade into the ordinary reality we experience, the hidden bridge between the haze of probability and the solidity of daily life. A mainstream fact is that quantum states are delicate. An electron or photon can remain in superposition so long as it's isolated, but the moment it interacts with its surroundings, air molecules, photons, vibrations, it loses that delicacy. The quantum wave function spreads out, but contact with the environment makes it collapse into a definite state. This is decoherence, and it happens constantly, invisibly, ensuring that the macroscopic world does not dissolve into uncertainty. A lesser-known detail is that scientists have managed to delay decoherence in carefully controlled experiments. By cooling particles to near absolute zero, isolating them from stray radiation, and shielding them from vibrations, researchers can keep atoms, ions, or even small molecules in coherent states longer than seemed possible. These efforts underpin quantum computers, which require qubits to remain in superposition and entanglement before decoherence washes the information away. The world of technology is learning to hold on to quantum fragility, if only for moments. And yet, the deeper meaning of decoherence is still debated. Does it fully explain the transition from quantum probability to classical certainty? Or does measurement itself play a role beyond environmental influence? Some interpretations argue that decoherence is enough, while others insist it leaves unanswered questions about why we see only one outcome when many remain mathematically possible. The discussion remains open, quiet, but unresolved. To imagine decoherence gently, think of morning mist on a field. At dawn, the mist covers everything, soft and uncertain. As the sun rises, the mist fades and the landscape appears sharp and clear. The quantum world is like that mist, full of possibility. Decoherence is the warming light that makes one reality emerge from many, leaving the others to dissolve into invisibility. This does not mean quantum rules vanish when decoherence takes hold. They are still there, guiding the bonds of atoms, the flow of currents, the spark of stars, but their fragile superpositions no longer reach our senses. The velvet sky we see each night is, in a way, a record of decoherence, vast quantum states settled into galaxies, stars and planets, and still, in the quiet spaces of the cosmos, coherence lingers. In the vacuum between stars, isolated particles may drift in superposition far longer than they could on Earth. In the cold silence of interstellar clouds, delicate quantum states might stretch across unimaginable timescales. The universe itself may be a vast laboratory where coherence and decoherence play out in slow balance. Here on Earth, our ability to preserve coherence is growing. Quantum computers, quantum sensors, quantum communication, all are attempts to hold on to fragility a little longer, to hear the whispers before they fade. It is a reminder that the boundary between the quantum and the classical is not absolute, but a matter of care, time, and connection. As we rest under velvet skies, decoherence becomes more than a technical term. It is a gentle reassurance that the world holds steady, that we can rest our heads on a pillow, that stars appear fixed in their places. Behind that stability lies the fragile shimmer of quantum possibilities, always present but softened, always humming but hidden. In this, we glimpse a harmony. The universe is both uncertain and certain, both fragile and strong. Decoherence is the bridge, the quiet process that lets us live in solidity, while the quantum haze continues beneath. And so we breathe, aware that beneath every moment lies a deeper fabric, fading and forming, like starlight dissolving into dawn. When we think of galaxies, clusters, and the cosmic web stretching across billions of light years, it is easy to forget that their origins are rooted in the smallest scales. Quantum fluctuations, stretched in the early universe, guided the formation of the vast structures we see today. From quanta to galaxies, the story of the cosmos is a bridge from fragility to immensity. A mainstream fact is that matter in the universe is not spread evenly. It gathers into filaments and nodes, leaving great voids in between. This web-like pattern has been mapped by large surveys such as the Sloan Digital Sky Survey, showing a structure that resembles a delicate lacework of galaxies. Computer simulations of cosmic evolution, starting from quantum fluctuations measured in the cosmic microwave background, reproduce this same pattern. The match confirms that the universe's largest features grew from the tiniest seeds. A lesser-known detail is that the faintest dwarf galaxies may hold some of the clearest traces of this origin. Unlike massive galaxies that undergo mergers and violent starbursts, dwarfs can remain relatively simple. Their distribution and dynamics preserve the fingerprints of the earliest quantum fluctuations, offering astronomers a kind of fossil record of structure formation. Studying them is like listening for the quietest echoes of the universe's first breath. And yet, the debates remain open. Astrophysicists still puzzle over the role of dark matter in shaping the cosmic web. We know that dark matter outweighs ordinary matter by a factor of about 5, and that it gathers first, pulling gas into its gravitational wells. But is dark matter composed of particles yet undiscovered, or is it a sign that our understanding of gravity is incomplete? The answer is still uncertain, and the structure of the cosmos hangs in that balance. To imagine this gently, think of frost spreading across a window pane. It begins as tiny specks, then grows into branching patterns, filaments reaching outward, delicate and intricate. The cosmic web is like that, but on scales beyond comprehension, guided by rules that began with quantum ripples. The Milky Way itself rests on one filament of this web, part of a local cluster called the Virgo supercluster, which in turn is part of an even larger structure known as Laniakea. These names give us anchors, but the truth is that we live within a vast flow, galaxies drawn together by gravity into patterns written by ancient quantum fluctuations. Even the stars we see each night are part of this story. Their placement, their clusters, their spiral arms are all shaped by the distribution of matter on large scales. The quiet shimmer of the night sky is not random, but an expression of order that began in probabilities. And here on Earth, every breath you take belongs to this pattern too. The elements in your body were forged in stars, stars that formed in galaxies, galaxies that gathered along filaments, filaments that arose from quantum seeds. You're not separate from the cosmic web. You're one of its threads. As we breathe beneath velvet skies, it is humbling to feel that connection. From the smallest fluctuations to the larger structures, the universe has grown seamlessly, without pause, without rupture. Fragility gave rise to strength, uncertainty to stability, quanta to galaxies. Perhaps this is the quiet lesson of the cosmic web, that even the faintest whispers can become vast harmonies, that what begins in fragility can sustain worlds, that the smallest seeds can blossom into horizons beyond measure. Here on Earth we live in a time when the quiet rules of quantum physics are not only studied in thought experiments or cosmic theories, but are being woven into technology. For centuries we built machines guided by classical physics, using levers, wheels, and engines. Now we are learning to work with the fragile principles of quanta themselves, coaxing them into devices that may reshape our future. A mainstream fact is that quantum computers are no longer only imagined. Prototypes already exist. Unlike classical computers, which use bits that can be either 0 or 1, quantum computers use qubits, which can rest in superposition, being 0 and 1 at the same time. When entangled with one another, qubits can perform calculations across many possibilities at once, solving certain problems far faster than any classical machine. Though still delicate and limited, these devices mark the first steps into a new era of computation. A lesser-known detail is that quantum sensors may have an even broader impact in the near term. By exploiting the sensitivity of quantum states, these sensors can detect changes in gravity, magnetism, or time with astonishing precision. Some are being developed to map underground structures, to detect gravitational anomalies, or to navigate without satellites. Others aim to measure time so precisely that even the slow drift of tectonic plates or the influence of dark matter might one day be traced. And yet, the path forward is uncertain. Quantum states are fragile, prone to decoherence, and easily disrupted by the environment. Building machines that can maintain coherence long enough to be useful is one of the greatest challenges in modern science. Researchers debate which approach, trapped ions, superconducting circuits, photons, or other designs, will prove most stable. The outcome remains unknown, and the future rests on questions still unanswered. To imagine these technologies gently, think of fireflies in a dark meadow. Each glows briefly, fragile and flickering. If they can be coaxed to blink together, they create a pattern of light more stable, more powerful than anyone alone. Quantum devices try to do something similar, aligning fragile states long enough to create harmony before the night scatters them again. Already, quantum technology connects back to the velvet sky above us. Atomic clocks based on quantum transitions keep time so precise that they guide satellites in orbit and allow us to navigate the Earth with accuracy down to meters. Without them, GPS would drift, and the world's maps would unravel. These clocks rely on electrons shifting between energy levels, a process rooted in quantum certainty and probability. And as we dream of the future, quantum communication beckons. Entanglement may allow information to be shared across distances with security that no eavesdropper can break. Photons entangled in pairs could carry messages that dissolve if intercepted, a quiet assurance written in the rules of physics. Experiments have already shown this across satellites in orbit, linking Earth-bound stations through quantum light. The debates about meaning continue, even as the machines advance. Does technology reveal the true essence of quantum physics, or are we simply learning to use patterns we do not yet fully understand? Some argue that the very success of these devices shows the reality of superposition and entanglement. Others remain cautious, suggesting we're still only scratching the surface of what quanta mean. For us tonight, it is enough to rest with the knowledge that the universe's smallest rules, once thought strange curiosities, are now shaping the tools of tomorrow. The same principles that guide starlight across the cosmos may soon guide communication, navigation, and discovery here on Earth. As we breathe under velvet skies, quantum physics no longer feels distant. It is arriving quietly, woven into our instruments, our clocks, and our future. Fragile as it may be, it offers a reminder that even the smallest whispers can change the shape of horizons. As we drift deeper into the quantum world, we find not only experiments and facts, but also interpretations, different ways of understanding what the mathematics is telling us. The equations of quantum physics work with exquisite precision, yet what they mean remains uncertain. For nearly a century, physicists and philosophers have debated how to read the whispers of probability. A mainstream fact is that the Copenhagen interpretation, shaped by Niels Bohr and others, remains one of the most widely taught. It suggests that quantum states exist as probabilities until they are measured, and that the act of observation collapses the wave function into one outcome. This view emphasizes the limits of knowledge and the role of measurement in defining reality. A lesser-known detail is that the many worlds interpretation offers a very different picture. First proposed by Hugh Everett in the 1950s, it suggests that the wave function never collapses. Instead, all possible outcomes occur, branching into parallel universes. When you measure a particle, you see one result, but other versions of you see the others, each in its own world. Though it sounds like science fiction, many serious physicists study this interpretation, and it provides a consistent, if unsettling, way of avoiding collapse. And yet, there are still other voices. Pilot wave theory, for example, proposes that particles always have definite positions, guided by hidden waves we cannot observe directly. Objective collapse models suggest that wave functions collapse naturally after reaching a certain scale, without requiring observation at all. Relational interpretations say reality is not absolute but depends on interactions, with each observer holding a different account of events. The debates remain unresolved. Astrophysicists and philosophers alike still ask whether quantum mechanics describes reality itself or only our knowledge of it. Some argue that the mathematics is enough, that seeking deeper meaning may be unnecessary. Others believe that until the interpretation is settled, our understanding will remain incomplete. To imagine this gently, think of a soft melody played on a piano. You might hear it as a lullaby, someone else as a hymn, another as a memory of childhood. The notes are the same, but the meaning varies with interpretation. Quantum physics is like that. The equations are clear, but the story they tell depends on how we choose to listen. Even in the cosmos, interpretations matter. If many worlds is true, there may be countless versions of the universe, each with different histories. If pilot waves are real, then hidden structures may ripple beneath space itself. If collapse is objective, then the universe chooses outcomes without us. Each possibility leads to a different vision of reality, and yet none has been proven beyond doubt. For us tonight, perhaps the uncertainty is itself the gift. We are reminded that knowledge is never final, that mystery is not a failure but a companion. The fact that physicists still debate these questions shows how open the universe remains, how gently it invites us to wonder. As you breathe beneath the velvet sky, you may feel the comfort of not needing to decide. The stars shine regardless of interpretation. The laws hold even if their meaning shifts. The universe continues, whether in one world or many, whether collapse is real or imagined. Perhaps this is the deepest whisper of quantum physics, that certainty is not required for beauty, and that mystery can be as restful as knowledge. At last, we arrive at the quiet horizon of our journey, where quantum physics meets the ultimate fate of the cosmos. The smallest rules, whispered in particles and probabilities, may shape how the universe ends, whether in fire, in ice, or in silence. A mainstream fact is that the universe is expanding and not slowing down. Distant galaxies drift away faster and faster, pushed by what we call dark energy. If this continues, the cosmos will thin out, stars will fade, and the night sky will grow darker over trillions of years. Eventually, only the faint glow of cooling remnants will remain, and even black holes may evaporate through Hawking radiation. The end, in this view, is not sudden, but a slow fading into quiet. A lesser-known detail is that quantum fields may hold the key to this future. If dark energy is tied to the vacuum energy of space, its value could change. Some theories suggest a gentle decay, where the expansion slows or even reverses. Others imagine a sudden shift, where the vacuum state changes and the laws of physics themselves transform. Such events are speculative, yet they remind us how much the smallest scales may decide the largest horizons, and still debates remain. Will the cosmos expand forever, tearing galaxies apart in a big rip? Will it cool into darkness in a heat death? Will it collapse into a big crunch, or bounce into new beginnings? Astrophysicists do not agree. The equations leave room for many endings, and perhaps many cycles. The truth may be beyond our horizon, waiting in the deep silence of time. To imagine this gently, picture a candle burning low. Its flame does not vanish all at once, but dwindles, flickers, and finally fades into darkness. The universe may do the same, not with drama, but with patience, a quiet sigh after eons of light. Even black holes, those dark engines of gravity, may glow faintly and dissolve, leaving only radiation drifting across empty space. And yet, in that silence, the quantum world remains. Fluctuations never vanish entirely. Even in the emptiest vacuum, there is still a hum, a breath, a possibility. Perhaps new universes could bud from these fluctuations as ours once did. Perhaps the end of one story is the beginning of another, written in the same quiet script. As we rest beneath the velvet sky tonight, it may feel strange to think of endings. But endings are not only loss, they're also transitions, moments where silence opens space for something new. The universe began in such a silence, and it may return there. Between those two hushes we live, breathe, and wonder. And so our journey through quantum physics comes to a close. From uncertainty to entanglement, from tunneling to cosmic dawn, we have drifted across scales from the fragile to the vast. What we found was not chaos but quiet harmony, a universe that is both uncertain and ordered, both fragile and strong. The cosmos may end in silence, but it began with a whisper, and tonight that whisper is still with us, carried in starlight, in atoms, in every breath you take. Now, as our exploration slows, let us drift gently into stillness. We have wandered across the smallest scales, where particles shimmer in uncertainty, and across the largest horizons where galaxies spread into darkness. Along the way, we have seen how fragility becomes strength, how whispers become stars, how uncertainty becomes the ground of stability. The velvet sky above holds all of it, ancient light from galaxies long gone, quiet echoes of quantum fluctuations from the dawn, the faint hum of the cosmic microwave background. Together they weave a lullaby of deep time. You are part of that song, your atoms born in stars, your breath carried on the same rules that guide starlight. Let the images settle softly. Imagine the hush of space, the slow drift of galaxies, the shimmer of photons crossing unimaginable distances. Picture the unseen hum of vacuum fluctuations, the threads of entanglement stretching across horizons, the the quiet certainty of atoms holding you in place. The universe is vast, yes, but it is also close. Its whispers are within you, shaping every thought, every heartbeat, every breath. As you lie here now, you can let go of questions. The debates of physicists, the puzzles of cosmology, the uncertainties of theory, they can wait. What remains is the comfort of mystery itself, the awareness that not all must be solved to be beautiful. Breathe slowly and let the night carry you. The stars are steady above, the universe unhurried, time itself softened into silence. You're safe within its vastness, held in its patterns, part of its story. And as sleep approaches, may the whispers of quantum physics fade into dreams, gentle and unbroken.